Hey guys, today I'll be going over the Chapter 1 practice questions from the 2014 Pearson IB Chemistry HL textbook. Chapter 1 includes no HL topics, so these questions should be the same for both SL and HL students. This chapter is extremely fundamental to the rest of the year, so it's imperative you understand what's going on in it. If there are any questions you had about Chapter 1 questions, hopefully I can answer them today. Good luck on your tests and exams. Now let's get started. How many oxygen atoms are in 0.1 moles of hydrated copper sulfate? So first let's count out how many oxygen atoms there are in this compound. So we see there are 4 here plus 5 right here. So we have a total of 9 oxygen atoms per particle of this compound. Now if we're talking about it in terms of moles, then we have 6.02 times 10 to the 23 particles of hydrated copper sulfate if we have 1 mole. And in each of those particles there is 9 oxygen atoms. However, we have 0.1 moles, so we have a tenth of this many oxygen atoms, which if you run through your calculator should be 5.42 times 10 to the 23 oxygen atoms, which we can see is D. What is the sum of the coefficients when the following equation is balanced using whole numbers? So first with this equation, let's just notice how there are oxygen atoms on both sides, so we may want to focus there first. Also notice how the oxygen atoms here are in an even number, so we'll want an even number on this side as well. So let's try 6 oxygen atoms. So we could do 3 there and 3 there, and we have 6 oxygen atoms here and 6 here. And the carbons are also both present on the same sides, so that makes it pretty simple. They're kind of bound together, so we would want both of these coefficients to be the same. Now the iron, we see there are 2 over here, so we'll also want 2 here. And it happens to be that that just works out. So we have 2 irons on each side, 3 carbons, and 6 oxygens. So if we do 1 plus 3 plus 2 plus 3, then we get 9. 4 identical containers under the same conditions are filled with gases as shown below. Which container and contents will have the highest mass? So since we see this phrase same conditions here, we can assume that all of these have the same temperature, volume, and pressure of gas. So then what we're really looking for is which of these gases has the greatest molar mass. So what we want to do is write out all of these compounds and figure out their molar masses. Ethane would be C2H6, because eth would be 2 carbons and then 6 hydrogens because they're all single bonded, and then neon would just be Ne. So N2 would be 14 times 2, which would equal 28 grams per mole. Now let's check out oxygen. Oxygen would be 16 times 2, which equals 32 grams per mole. Ethane, we have 2 carbons, so that would be 12 times 2 is 24, plus 6 hydrogens. 6 times 1 equals 30 grams per mole. And then neon is fairly small at about 20 grams per mole. So then the greatest one of these is oxygen, and so B is our answer. 1 cubic decimeter of an ideal gas at 100 kilopascals and 25 degrees Celsius is heated to 50 degrees Celsius at constant pressure. What is the new volume in cubic decimeters? So what should stick out to us here is an initial volume, an initial temperature, a final temperature, and a final volume. So we may then want to use, since we have volume and temperature, and a shift in one of them, Charles' law, which relates volume and temperature together when you change one. So we have the original volume of 1 cubic decimeter over the original temperature in Kelvin, so we would then have to do 25 plus 273 to convert, which will be 298. Then we're trying to find the volume, so we'll just leave that as V2. And then the second temperature is 50 degrees Celsius, which is 50 plus 273, which is 323. And then we have V2 equals 323 over 298, which is about equal to 1.1, which is C. What is the amount in moles of sulfate ions in 100 cubic centimeters of 0.02 moles per decimeter of iron sulfate? So let's pull out our most relevant formula here, which is moles equals concentration times volume. So we're given our volume in cubic centimeters, but we're given our concentration in decimeters or moles per decimeter. So we're going to want to convert this 100 cubic centimeters to decimeters. So we'll say N equals 0.02 for the concentration, then for the volume. Since there are 1,000 cubic centimeters in a decimeter, we'll divide that by 1,000. And then we'll have 0.002 moles of iron sulfate. Now, since there is one sulfate ion per particle of iron sulfate, it's just a 1-to-1 ratio. So we still have this many moles of sulfate ions. So this equals 2 times 10 to the negative 3, which is A. 1.7 grams of sodium nitrate is dissolved in water to prepare 0.2 cubic decimeters of solution. What is the concentration of the resulting solution in moles per decimeter? So this would probably be an N equals CV problem with moles, concentration, and volume. Now we're looking for the concentration, so let's instead rewrite this as concentration equals moles over volume. Now we have 1.7 grams with a molar mass of 85 grams. So then the number of moles of sodium nitrate would be 1.7 divided by 85. And our volume is 0.2 cubic decimeters. Now it turns out this here is just equal to 0.02 divided by 0.2, which equals 0.1 as the concentration. And then we have that as an answer here, B. What mass in grams of hydrogen is formed when 3 moles of aluminum react with excess hydrochloric acid according to the following reaction? So let's focus on the aluminum and the hydrogen here, since that's what the problem is asking us about. So what we can interpret this as is for every 2 moles of aluminum, we'll get 3 moles of hydrogen in the reactants if we have excess hydrochloric acid. So if we have 3 moles of aluminum, then that just means these 3 moles will react in a 3:2 ratio. So what we'll end up with is, make this a little easier to see, 2 moles of Al, those units cancel, and we'll end up with 4.5 moles of H2. Now, the molar mass of H2 is about 2 grams per mole. So 4.5 times 2 equals 9 grams. And then we have our answer. The relative molecular mass of a gas is 56 and its empirical formula is CH2. What is the molecular formula of the gas? So if we sort of think about our definitions of empirical and molecular formulas here, we might realize that the molecular formula is just the empirical formula with a certain multiplier. So what we want then is to figure out what that multiplier is. So we can do that by taking the molar mass of the empirical formula. So it would be 12 for the carbon plus 2 for the hydrogens equals 14. Now, since we're told that the relative molecular mass is 56, then we can find the multiplier by taking that mass and dividing by 14, which it turns out is 4. So then, we apply that multiplier to the original empirical formula here. You can think of it that way if you'd like, and then you'll end up getting C4H8, which is D. What is the sum of all coefficients when the following equation is balanced using the smallest possible whole numbers? So it's just a balancing equations problem, so we sort of have to just keep guessing and checking until we get it right, but we can still observe a few things. So usually when you have oxygen by itself in a combustion reaction like this, you're going to want to leave that until the very end. It usually just works out better. Let's also notice how these two carbons are sort of bound together here. So we want to make sure that these two coefficients match the carbons up nicely. So let's just try 2 and 4, which will keep the carbons in line here. Now let's look at the hydrogens. So there are 4 hydrogens with this 2. So we would also want 4 hydrogens here. And now we can finish up with the oxygens. So we have 8 oxygens and then 2 oxygens here for 10. So we would need a 5 there for 10 on this side. And then we have 2 plus 5 plus 4 plus 2, which equals 13. And so the answer is D. What is the total number of hydrogen atoms in 1 mole of benzamide? So let's write out this molecule. Now since it's asking us about the hydrogen atoms, let's focus in on those. So we have 5 plus 2 hydrogen atoms means we have 7 hydrogen atoms per molecule of benzamide. And since there are 6.02 times 10 to the 23, in this case, molecules in a mole of benzamide, in each of those, there's going to be 7 hydrogen atoms. So if we evaluate that expression, then we'll get 4.2 times 10 to the 24th hydrogen atoms per mole, which is D. Chloroethene C2H3Cl reacts with oxygen according to the equation below. What is the amount in moles of water produced when 10 moles of chloroethene and 10 moles of oxygen are mixed together and the above reaction goes to completion? So here we have a limiting reactants problem. So what we're going to want to do is take each of these reactants and figure out which one is the limiting one, which one will get used up first. So we can do that with molar ratios, and since we've already been given these in moles, we don't have to do any gram to mole conversions. We can just jump right into it. So if we have 10 moles of ethene, or chloroethene, excuse me, then based on these molar ratios, because 2 moles of C2H3Cl will react with 5 moles of oxygen, that ratio will mean that we need 25 moles of oxygen for this reaction to go to completion. So we don't have 25 moles of oxygen, so instead we would base our stoichiometry on how much of this reactant reacts. So now we have 10 moles of oxygen instead. These would react in a 2 to 5 ratio, and we would get 4 moles of chloroethene. Now we can base our stoichiometry on this discovery here, that we're only going to use 4 moles of this substance. Now, since these react, the water was what we're looking for, the water reacts in a 1-to-1 ratio with the chloroethene, we can say that with 4 moles of chloroethene, we would also produce 4 moles of H2O, because 4 times 2 over 2 still equals 4. And so we have 4 moles of water, and so the answer is A. What is the concentration of sodium chloride in moles per cubic decimeter when this solution and this solution are added together? To make it a little shorter and save time instead of reading all that out. So let's look at our givens here. What we're really going to want to do is eventually add up the moles of NaCl in each of these solutions and then divide it by the total volume, which we can see right here and here. It'll eventually be 40 cubic centimeters. So to begin, let's just remember N equals CV. So then N total will equal N1 plus N2, the number of moles of sodium chloride in the first solution and the second solution. So what we can then do is say N total equals, the first concentration is 0.2 with a volume of 10 cubic centimeters, which we'll have to convert to decimeters so that the units agree with each other because the concentration has decimeters. And then we'll add the second solution, 0.6 times 30 over 1,000 to convert again. And if you work out this expression in your calculator, you should get 0.02. Now, this is moles of NaCl. Now, we can rewrite this. Instead of N equals CV, we're going to want V equals N, or excuse me, we would want C equals N over V. So then we can say C equals 0.02 moles of NaCl we found here, divided by the volume, which is going to be the sum of these two volumes up here. So we would then have 10 over 1,000. Actually, we can just combine these together. 10 over 1,000 plus 30 over 1,000, which is going to be 0.02 divided by 0.04, and that equals 0.5 for the concentration moles per decimeter cubed. And then our answer would be C. On analysis, a compound with a molar mass of 60 grams per mole was found to contain 12 grams of carbon, 2 grams of hydrogen, and 16 grams of oxygen. What is the molecular formula of the compound? So first we're going to want to find the empirical formula and then try to get to the molecular formula by finding sort of N, what we would have to multiply by to get from the empirical formula to the molecular formula. So let's take each of these masses, 12 grams of carbon, 2 grams of hydrogen, and 16 grams of oxygen, and then divide these each by their molar masses. 12 grams per mole, 1 gram per mole approximately, and 16 grams per mole. And so then our empirical formula will have 1 mole of carbon, 2 moles of hydrogen, and 1 mole of oxygen, which we can represent as CH2O. Now, if we want to find the molecular formula, we would want to find the molar mass of this compound and then find what we have to multiply by to get 60 grams per mole. So the molar mass of this compound we can say is 12 for the carbon, plus 2 for the hydrogens, plus 16 for the oxygens, all in grams. And then if we add these up, we would get 30 grams per mole. And the molar mass of this compound that we're analyzing is 60 grams per mole. So then we would have to multiply all of these by 2, and we would have that molar mass. So then the molecular formula would be C2H4O2, which is D. 300 cubic centimeters of water is added to a solution of 200 cubic centimeters of 0.5 moles per cubic decimeter of sodium chloride. What is the concentration of sodium chloride in the new solution? So we'll want to use one of our dilution formulas, either M1V1 equals M2V2, or more preferably, since in IB we like to use moles and cubic decimeters rather than liters, C1V1 equals C2V2. Regardless, you'll probably get the same thing using either of these equations because they both imply the same thing. So now since we're trying to find the new concentration, we can take that to be C2 in this equation. So if we solve for C2, we'll get C1 times V1 divided by V2 equals C2. So now we can just plug and chug to get our answer. So C2 equals the initial concentration, which is 0.5 moles per cubic decimeter, times 200 cubic centimeters, which we'll have to convert to cubic decimeters. And now we're dividing by the final volume of the solution, which is going to be 300 plus 200 cubic centimeters. Convert that to decimeters, divide by 1,000. Now conveniently in this case, since we have an 1,000 both up here and down here, these actually cancel to make the math a little easier if we multiply by 1,000 over 1,000. So just a little shortcut you can use. So then we'll end up with 0.5 times 200 is 100, over 300 plus 200 is 500, which is 0.2 moles per cubic decimeter. And so our answer is C. What is the approximate molar mass in grams per mole of hydrated magnesium sulfate? So this problem isn't very difficult. You just need to be careful of the subscripts and coefficients with the water to make sure you're not messing up any of your addition or multiplication, because at the end of the day, that's really all this problem is. So let's just go through this compound. MgSO4.7H2O. Alright, so Mg, molar mass of magnesium, is about 24. It's more like 24.3, but this will be fine for this problem. Then sulfur is 32. Then it's 4 oxygens, so 16 times 4. And then we have this as well, right here, 7 water. So 7 times 2 hydrogens means 14 hydrogens, which is about, just to stay consistent, we'll do 1 times 14. And then 7 oxygens would be 16 times 7. So now let's simplify all of this. Let's simplify all of our multiplication. And we'll get 24 plus 32 plus 48, or not 48, excuse me, 64, plus 14 plus 112. So now it's just addition. So 24 plus 32 is 56. Plus, let's say 64 plus 14 is 78, plus 112, 56 plus 190, whoops, 190, and then we get 246, which sure enough is D. Which is both an empirical and a molecular formula? So for it to be empirical and molecular, we would need one of these to not simplify down any further. So let's just draw each of these out. This one does not simplify, so this one is most likely our correct answer, but let's keep going. This one will simplify to CH5, this one can simplify to CH4, and this one to C2H5. But this one cannot simplify at all, so it is empirical and molecular, so then we can say it's A.